Hi everybody, good morning. Hello, I'm just going to give everybody a couple of seconds to arrive. Fabulous. Okay, fantastic. So, hi everybody, welcome to our latest Spring Knowledge Showcase. This is on continuous remote pipeline monitoring using Optic Fibre with Scottish Water partnering with Xylem and WRc to monitor the condition of Blairlinnans trunk main using SoundPrint acoustic fibre optic system. My name is Imelda Fosu and I am the Comms and Engagement Manager at Spring. So I just want to tell you a little bit about Spring and our knowledge showcases. So Spring is the UK Centre of Excellence for Water Innovation in the UK. We're an innovation accelerator that enables collaboration within and beyond the water sector to drive transformational innovation. We are very proud to be funded and able to represent all of the 19 UK and Ireland water companies with further sector stakeholders in supply chain, academia and startups. Really excited to be doing this showcase today, Scottish Water, Xylem and WRc, on a very exciting project. The reason why we kind of like to put these showcases together, so this falls under our knowledge transfer service offering. We like to do a range of things under our knowledge transfer service. So this is all around doing showcases such as these, a kind of 2-hour deep dive into innovation projects. And also we have case studies. So at the end of this showcase is being recorded, it will be going onto our Spring platform alongside a case study. So you can share it with colleagues and you can view it afterwards. So I'm just going to go over the speakers for today. So you have myself as a Comms and Engagement Manager. Also, I'm happy to have Andrew Dunbar, who is the Water Service Strategy General Manager at Scottish Water. We have Warren Beer, who is the Condition Assessment Engineer at Xylem. We're also joined by Ian Dunsmore, who is the Team Leader of Strategic Water Infrastructure at Scottish Water. And we have Anthony Bond, who is the Technical Manager at the Water Research Centre. So I've got a really great lineup of speakers for everybody today, and they'll be fantastic to be able to tell you a bit more about this project. So I'm going to quickly go through the agenda. I'm going to hand over to Andrew. So for the agenda today, we are going to have a quick word from Andrew Dunbar, who's the General Manager of the Water Service Strategy. We're then going to go into a section with Ian, and he's going to talk about the product identification. We're then going to have a little bit from Ant, and they'll be talking through the pipeline surveys, and then Warren will be taking us through the engineering analysis of the project. Then we'll have a short kind of 10-15 minute coffee break, so a chance to kind of stretch your legs, but please don't log off because then we'll be coming straight back and we'll be talking with Warren about the AFO system, and Ian will be going through the outcome of the project, and then we'll have some chance for Q&A. So the chat is open. Please feel free to drop questions in throughout the session, and these will all be picked up in the Q&A section at the end. So we'll probably give it a thumbs up or a like just to show you that we've seen it, and then these will be picked up after the break in the Q&A section, but please do feel free to put your questions in the chat and we'll be collating them throughout today's session. Okay, so without further ado, I'm going to hand over to Andrew Dunbar, and he is going to give you a little bit of an intro from his side from Scottish Water. Andrew, over to yourself.
Thank you. Hello everybody and welcome to sunny Edinburgh. Can't see out the windows unfortunately. I'm Andrew Dunbar, the General Manager for Water Service Strategy. We are the team that effectively undertake all assessment of risk and then promotion of ongoing investment into the water supply systems across Scotland. Today you're going to hear from one of my team, Ian, who's been running this project, particularly looking at Blairlinnans, the support from Anthony and Warren from our supply chain partners. And I'd like to thank them all today for coming along to do this. It's always great to share the knowledge that we've learned, and we've learned a lot on this project. To provide some context to what we're going through today, we operate around 5 pre-stressed concrete pipeline systems in Scotland, covering around 81 kilometres in length. Most of these were built in the 1960s as part of regional schemes that were installed in those times. In 2014, we started to get a bit of a concern, particularly looking at what was going on in the States in relation to failures on these pipelines, the catastrophic nature of them, and the links there into the wire corrosion and just the difficulty to therefore repair. So we began a programme then of understanding them and then inspecting and following on. To date, we've inspected 3 of those pipelines. Blairlinnans has been one of them, and probably the most complicated to do. And it's provided a lot of learning, which will be shared today as we go through. You may notice that 7 years that we've been at this, so it does show the amount of time it takes to accumulate that knowledge and go through it. Hopefully you'll enjoy today's presentations, and what I'll do now is I'll hand it over to Ian, who will take you through more detail.
Morning everyone. I'm Ian Dunsworth, I'm the Strategic Water Infrastructure Team Leader. I'm going to take you through the project identification. So, in Scottish Water, our asset management strategy is driven in large part due to the way we are owned and funded. We are completely owned by the Scottish Government. They are, if you go above Andy, his boss eventually becomes the First Minister of Scotland if you go high enough. So we have what are called ministerial objectives from them. One of those, and the key one of those, is to maintain or improve levels of service. This may sound like, maintaining level of service may not sound like a very stretching goal, but as prices go up, climate change adaptation hits in, just maintaining where we are can take a lot of effort and a lot of time. So to actually improve levels of service can be a bit of a challenge on top of that. Just, sorry, the screen, I can't see what's that. Sorry, I changed anyone. So part of that objective is to develop an evidence-based strategy. So everything we do needs to be based on fact. We have to be able to demonstrate the condition of an asset, what the impact of that asset will be, should it fail, and how we're going to manage that asset. We can't go on anything other than an evidence-based strategy now, which is the way things should be. And a big part of that is about how assets are critical to maintaining service delivery to our customers. And I think the key point of this slide is it must command confidence of our regulators. We have developed a very good relationship with our regulators in Scottish Water, to the point that we are now funded in a way that I'm going to talk about shortly that is different to what we have been in previous investment periods. So our risk appetite, the table on the right, I'll come on to in a minute, but we've adopted a series of management approaches. Now these are based on asset groups, so the one I look after is ME025, which is strategic infrastructure. There's elements of it with other team leaders, but the majority is mine. And what we do here is we set out condition and so likelihood of failure and consequence of failure. We monitor every main against those. We then say, should the likelihood and consequence be such, so the likelihood and impact scores that are on the table there, if it's a P0, P1 or P2, we will invest in that asset. These threshold values are reviewed because it's a new process in Scottish Water. It's only since the SR21, so 2 years we've been running this way, and there will be an element of calibration involved in that. So we review them on a regular basis to see if we're over promoting, under promoting. If there's projects that are not being promoted that we think probably should be, we then look at, are we measuring against the right things? One of the key things this gives us is some flexibility. Previously, we would go into an investment period with a list of named projects, and these are the named projects we're going to do in this investment period. Now we go in on the basis of these are the thresholds we're going to promote against. So if a project meets those thresholds, even if we had something else planned but a more urgent need comes up, we can go and work on the more urgent problem without having to go back and try and say, well, we're going to remove this project from our plan and do it. That flexibility is going to be key as there's ever emerging new needs become apparent. So why Blairlinnans and why this pipe? Pre-stressed concrete pipes are comparatively rare. Like Andrew said, we have a comparatively very small number of them in Scottish Water when you look at our entire asset base. I have like 6,000 kilometres of trunk mains, of that 80 kilometres of it's pre-stressed concrete. So it's a tiny fraction. This particular main feeds a large number of customers. There's a proximity risk for a small number of properties that are fairly close to where the pipe is. Key ones is we have very limited resilience options. With the geographic nature of the system where it is, we don't have other treatment works nearby that we can connect into should we need to. If this pipe fails, that is the sole supply to a number of customers. So we're doing a separate project to look at increasing this resilience, where we are going to put in some cross-connection links that would improve that. But the first stage is to get a better understanding of this pipe, its condition, its performance, and how we manage that over time. As Andrew's already said, pre-stress is a lesser used material. We don't have a great deal of experience dealing with it, which is why we went to partners, such as WRc and Xylem, who have significantly more experience dealing with these kind of pipes. And we're looking at creating an industry standard for how we manage them going forward from here. There are also some significant transport risks associated with this main. We have major railway lines, major roads that would be affected potentially should it fail. So it is key that we make sure that we're on top of the condition of this pipe and intervene before it gets to that point. We went through some an options assessment for this. So there's the do nothing option, obviously, which is not an option. One of the options we looked at was buying the houses that are in proximity to the pipe. This was rejected for a number of reasons, but there's serious reputational risks involved in that. We looked at some local replacements, partial replacement of the trunk main, full replacement of the trunk main, and then an inspect and monitor option. So, as you can probably imagine, 16 kilometres of large diameter pipe in the countryside and difficult to get to places is not going to be easy, cheap, or straightforward to replace. When we went through this list of options, as you can see on the right, again, which option meets which driver, proximity, resilience, and allow us to maintain the asset, the one that hit the most of these was really the inspect, monitor, and develop strategic approach. So that's where we got to as this is how we're going to go forward. Now that involved a significant period of work over a number of years. The inspections required to get a baseline of what the condition of the main is, so that we understand where we're starting from and we understand what the risks are, and we can then intervene appropriately based on those risks. I think I'm going to pass over to Dan now to talk about the pipeline surveys themselves.
So good morning, everybody. I'm Anthony Bond from WRC. I'm the technical manager for our condition inspection business. Been involved with this project since the outset, and I'll talk you through the inspection stages that we went through for the work. So back in 2015, we were successful bidders on the SR15 inspection and testing framework in partnership with Pure Technologies, as they were at that stage, now part of Xylem. And we partnered to offer the sort of assess and address condition assessment philosophy, effectively. So that is to inspect, look at the condition, and then analyse the options for how that pipeline, that asset can be managed in the future. What WRC were able to provide Pure, as they were at that stage, who were Canadian based, with a UK presence. We have survey solutions of our own that we offered. So the Sahara pipeline inspection system for leak detection, cameras, inspections, lots of other condition assessment technologies associated with that. Also able to provide local liaison, being UK based, that was an assistance for Pure, having people within the UK. Obviously, we're also, with WRC's got strong history in terms of technical background within the water industry, we're able to provide technical support and advice. And then Pure Technologies had really strong history in inspecting pipelines, North American based, large number of pipelines, really focusing on condition assessment, whereas in the UK, often the driver in the past has been leakage. In North America, the driver is much more around condition assessment, consequence of failure being a real driver for the North American companies. And Pure had developed a number of technologies, so we'll come on to those in a minute, but Smart Ball, Pipe Diver, AFO, all very much focused on inspecting large diameter pipes, and particularly relevant in this case for inspecting pre-stressed concrete pipe. So really strong background in that area, and able to therefore move straight into this project to provide really strong guidance on what was possible. So early outset of the SR15 framework, Scottish Water came to us and said, look, we've got this this pipeline that we need to understand how we go about managing it in the future. They'd carried out some very detailed assessments on what the consequences of failure of any section of that pipeline will be, and how it would be got back into service should there be a failure. So we're able to quantify the expenditure and the time frames of that, but had no real understanding at that stage of how likely was it that any of those failures should occur. So it's all very well understanding what you would do if it fails, but actually it's really quite helpful to know, is the thing in danger of failing? And actually, are there specific locations that are in danger of failing? And the kind of knowledge that Xylem were able to bring was the history from the North American experience, where large numbers of pipelines are pre-stressed concrete. So they were able to draw on that experience and show that actually the chances are you will have a pipeline and there will be very few individual pipes within that which have risk of failure. So understanding that and understanding where they are so that you can focus on those rather than talking about replacing the whole main is a really critical aspect. So there was a requirement to look at this pipeline. So we take the information that we have about that pipeline. So there were the original drawings, some original drawings, as so often the case in the UK, the drawings record is limited, and perhaps don't have to, as with all companies, we find that it's very rare to have really good detailed drawings, but we had some pretty good drawings in this case. We're obviously able to go out and carry out site visits and look at the assets on site, engage with the local operators and with more generally with Scottish Water operations to understand the real key aspects of this pipeline. And particularly to understand what are the restrictions that apply to this pipe. So if we're going to carry out any inspection work, what is it that we need to be bearing in mind the whole time that are factors that affect what Scottish Water is able to do in order to enable works in this pipeline. So critical things are the fact it's feeding customers. It's a live potable water main. So initially, immediately that throws up a number of factors that need to be taken into account. Now, both Pure and WRc have very strong history in inspecting live potable water pipelines. So that was a strength. The other critical thing, no interruption to supply, was a really key factor. So this is a large diameter pipeline feeding customers live, and there can be no interruption to supply. Those make inspecting pipelines really challenging, and I think we need to make sure we don't sort of forget that is critical and a real obstacle to what options are available. So the idea in this approach was to take the pipeline, a well-established technique from Xylem was to carry out a series of surveys of the pipeline to establish what its current condition is, and then move forward to, once you understand what is the condition of the pipeline at present, to what then do we need to do in the future to continue to monitor the condition of that pipeline and understand how its condition is changing over time. So there are two sort of key tools that we used in that process: Smart Ball and Pipe Diver. Smart Ball is a free swimming leak detection tool, primarily leak detection. We'll come on to the sort of details of it in a moment with a quick video and then some more in-depth chat about those surveys. But what it's able to do, identify leaks that are running at the moment. So identifying current risks to the pipeline. The other thing it's able to do is to prove the ability to get a free swimming device successfully from one end of the pipeline to the other. It's like a check of the planning work that's gone into the whole process. Then, following the Smart Ball survey, Pipe Diver, which is a true condition assessment tool, and this is the beauty of this tool in this case, is that it's specifically designed to carry out condition assessment of pre-stressed concrete pipe and tell you for individual pipe that makes up your pipeline what the condition of that pipeline, what of that pipe is. So not only identifies its condition, but tells you where it is. So you're able to identify clearly which individual pipes require work, which is a really important driver for and really helpful for future planning of any future works. What best remember is these tools are carried out. They carry out a survey. They take maybe a shift to pass the device from one end to the other. So they tell you the current condition of the pipe when you carry out the survey, but you're not getting any long-term information from it. So you're not building up anything in the future. But we'll come on to the techniques that can be used for that once you've carried out these initial surveys. Sorry, I didn't bring up the picture of Pipe Diver, but there we are. That's the Pipe Diver tool. So Smart Ball, the sphere in the foam jacket in the upper picture, and then Pipe Diver, the sort of full diameter tool that's in the lower picture. So we're going to have a quick video. I'm just going to run through the Smart Ball process. So how what the ball looks like, how a survey typically is operating. It just takes a minute and a half or so, but we'll just run through that, and I'll give you some talk about the tool. So the ball is about 60 millimeters in diameter, about the size of a tennis ball, sits inside a foam jacket. That catches the water and rolls it through the pipeline. Got a number of sensors inside it, an acoustic detection device, so a microphone, which logs the sound inside the pipe, and it's got a bunch of magnetic and a gyroscope in it as well. Launched into the pipe through an access point. We'll come on to the types of access that's used, using this claw device to squeeze it and allow it to be released into the pipeline. It'll travel through the pipeline with the flow. So clearly there are obstacles in the pipeline. We need to consider what those might be so that we can check that we understand that we can get the ball from the entry point to the extraction point. As it passes along the pipeline, if there's a leak, it's going to go right past it. So at that point, it's going to clearly detect the noise. We're going to log that in the SoundPrint, and we're going to be able to analyze that data afterwards and see where those are. There are a number of monitoring points put on the pipeline along its length, which allow us to track the movement of the ball. We'll talk about those in a bit more detail. And at the downstream end, it rolls into a net, quite simply caught and pulled back out through an access point into the pipeline. So a very simple process when you look at it in that way. Sorry, I've just noticed we've got a backup power light to come up on the computer here, so we might be just. Thank you. Sorry, just a minor technical issue here. The battery on the computer we're using to run the slideshow is wrong. So we're going to launch Smart Ball into the pipeline. Clearly what we need is an access point in order to be able to get the ball into the pipeline. On the Blairlinnans pipeline, we're lucky that there are air valves at frequent intervals along the pipeline. Each of those had an isolation valve below the air valve, so we're able to close the isolation valve, remove the air valve, and then install the Smart Ball launch assembly Launch assembly is very simple. It's just effectively a tube that's bolted to the top of the pipe and then sealed up with the smart ball in the claw that you can see there. Well, the ball being loaded in the middle picture, and then actually within the claw on the right-hand side, which is used just to squeeze the ball down, hold it, and lower it down into the pipeline. Clearly, we seal around the top of that assembly to stop the water escaping, so that we can open the valve, deploy the claw into the pipeline, and then when everything is ready downstream, we can release the ball and the survey is underway. One of the key factors is to make sure that you put the extraction net in the pipeline before you release the ball. So one of the first things is to make sure that that is deployed. Again, we're able to use an air valve for that deployment. So it just needs a 100mm diameter hole in the pipeline, access into the pipeline to deploy that device. So at the extraction point, we would turn up again, remove the air valve, put the extraction net on. Again, it has a seal around it, so we're able to open the isolation valve, push the net down into the pipe, and as you saw in the video, it opens up in the flow, and it's left there for the duration of the survey with a camera monitoring it to make sure that we can see what's going on, know that it's fully open in the flow, and that it's ready to capture the ball. Once that's in place, the ball can be released. Now, what I was slightly, the video was slightly quicker than I was able to keep up with, but there are a number of things that we need to ensure. Clearly, if you're releasing something into a pipeline, you need to ensure that it's going to arrive at the downstream end. And there are a number of reasons why it might not. So first of all, branch connections. So part of the planning process is to ensure that you look at all of the branch connections that come off that pipeline. You fully understand what flows are that come out of those, where they come off the pipeline. So if they come off the invert, if they come off the center line, or if they come off the top, it all makes a difference to the actions that may be required to ensure that the ball passes that without any incident. If they come off the top, very often you need to do very little. Just know that they're there. The ball is rolling along the bottom of the pipe. It's probably going to be unaffected by a branch connection off the top. If they come off the centre line, important to understand what size that branch connection is relative to the main pipe and what velocity of flow you've got coming out of it. If they come off the bottom, chances are you're going to need to close that branch connection, preferably for the duration of the survey, but not necessarily. It might be that you can have just a short closure as the ball approaches, close that branch connection. Once the ball has gone past, open it up, and the ball will be away downstream. Now, obviously, understanding where the ball is at any point is really quite important. And one of the beauties of the smart ball system from Xylem is the tracking locators that are used on the pipelines. These are small sensors that are glued onto the pipeline at intervals along the pipeline in advance of the survey. And then during the survey, a monitor is hooked up to that locator, and it monitors the passage of the ball past that location. Now, not only does it pick it up as the ball is going past, but it can actually hear the ball coming and see it going away down the pipeline. So we are able to understand for most of the survey where the ball has got to, where you can, as I say, you can see it several hundreds of meters upstream, several hundreds of meters downstream. You can see the ball coming and going away. Now, that has a couple of factors. One is during the survey itself, it gives you that confidence and security of knowing where the ball is, where it's got to, how it's moving. And the other thing is, once you're analysing the data, any features that you detect, so any leaks that you've detected, will be time stamped, and you'll know that you heard that feature at a particular time. And looking at the tracking data, you're able to say, and we know that at that time we were so many meters from that tracking location. So you can really accurately pinpoint where those features were, and therefore go and make the appropriate actions at that location. So I talked about features. One of the other things that was in the video that I didn't get a chance to mention was the fact it not only does it detect leaks, but it will also detect gas pockets, so air pockets in the pipeline, which clearly can have an impact on long-term condition. So the smart bore was of this pipeline was carried out in 2 sections. There was an intermediate branch feeding a large number of towns, which couldn't be closed. It was one of the factors that as we mentioned, mean this pipeline needs to remain live at all times. So the smart bore was launched, carried out a section of the upstream 9 kilometres, removed intermediate location, and then put back in again, and the survey continued. That was carried out on 2 successive shifts. So the 9 kilometre survey started mid-morning, was completed by late afternoon. Similarly, the following day, we carried out the second survey. Both surveys went absolutely without any hitches, so they showed the benefit of the planning, that we understood where the branch connections were. Steps had been put in place to ensure that there was no problems at those locations. And there was some features found. So three leaks were detected on the upstream section, and also one of the branch valves that was closed for the survey was actually passing slightly, so we were able to hear the water escaping under the valve. In the second section, there were 7. I've put potential leaks here because actually most of those were adjacent. Well, the signature came from a point where there was an air valve or a scour valve, so there were features that were leaking. So fittings on the pipeline that had a leak associated with them. So less critical in terms of the consequence or the likelihood of failure, because a fitting that's leaking is much less likely to be a source of failure than a leak that's coming from the actual the pipe joints or the barrel of the pipe. So following the smart bore survey, the next thing was to carry out the pipe diver surveys. Pipe diver, as I mentioned, is the condition assessment tool. It has a number of modules in it, which allow it to carry out the condition assessment, and basically it has a number of sensors around each of those fins or petals that are sticking out from the central body of the tool. Those give you, those monitor the condition of the pipe as it moves along the pipeline. And what it does is it's emitting a tone and emitting a signal, looking at that, and it allows it to count the number of pre-stressed wire breaks within each individual pipe of the pipeline. It can be deployed in a number of ways, but in this case we chose to deploy it through a connection point that could be depressurized. Once in the pipeline, as with smart bore, it travels with the flow, but this device is neutrally buoyant, so it floats within the middle of the pipe, kept nicely spaced off the walls by the petals. As it passes down the pipeline, if there are any broken wires within a pipeline section, the data is recorded and you get a signature from that can be analysed later to indicate the number and severity of the pipeline breaks that you've got in that particular point. As with the smart bore, it's tracked along using those locating devices, and at the downstream end, an extraction tool is used to capture the tool and pull it out of the pipeline while it's under pressure. The critical thing about this is that PCC pipes come in a range of different shapes and sizes and pressure ratings, and each one is different. So you have the way pre-stressed concrete pipe works is that you have a thin metal cylinder typically, and then with a concrete surround, and then the pre-stressing wires are wrapped around that, and the diameter, the spacing, and the tensions that those are under, and how many layers of those wires allow the different types, the different pressure ratings of pipe to be established. So for the particular survey, you need to make sure that the tool is set up to look for the specific range of pre-stressing wire that you can get, so that when you analyze the data, you can be sure that you are clearly analysing it, and that your data, you can correlate the signal that you see with the actual number of wire breaks that are associated with that particular pipe. So one of the first steps is to carry out a calibration. So in that case, the tool is passed through a dry pipe above ground, pass through, look at what the signature is from an undamaged pipe, and then by chiseling off the outer coating of concrete, actually cutting individual wires. You can see there on the right hand side, so there's a bunch of the wires have been cut And by cutting increasing numbers and passing the tool through a number of times, you build up a picture of the signature of those broken wires. That data is then fed back to the analysts, who can use that to make sure that when they analyze the data, they know what they're looking for. It also, as I say, lets you set up the tool to ensure that it's in the right range for the particular survey. So, having got the tool all set up, ready to go, you can see that on the bottom left there, the tool being set up. It needs to be set up for buoyancy, so adjust the buoyancy, adding flotations or weights to the actual tool itself to make sure that it is neutrally buoyant and just sits nicely within the centre line of the pipe. You can see there in the middle picture, we actually had a temporary swimming pool that we set up in the yard of one of the Scottish water sites. Filled it with some nice fresh Scottish water, and we're able to float the tool and ensure that it was perfectly balanced. And then the launch itself, as I mentioned, we launched this at a point that could be depressurized. In this case, it was a bypass. So on the outlet of the reservoir, the Blairlinnans reservoir, there's an outlet where the original pipeline runs straight down the hillside, but in previous years, a meter branch had been put in, so there was a connection coming off the side of the pipe through a meter and then back into the main line. The way that valves were situated allowed us to depressurize that meter branch. We were able to install a 300mm connection onto the top of the pipe, which could be depressurized, install pipe diver into the pipeline at that point, open up the valve connections and allow it to pass on down the pipeline. I mentioned the extraction tool. So this device allows us to extract the tool while the pipeline remains under pressure. It's quite a large device. You can imagine you've got a pipe diver tool which is of the order of sort of 3 meters long. So that has to be caught and pulled and extracted right back out of the pipeline. So it is a large tube that sits on top of the pipeline with a number of features that allow it to be moved in and out of the pipe. It's got quite a complicated device, but yeah, needed to be lifted into place with a crane because of the size of it, and actually in this case it's quite a large crane just because of just the operational swing and where there were relatively limited access to the side. Again, the extraction point is put in place prior to releasing pipe diver, so you make sure that that is in, deployed and monitored before you release pipe diver. So the pipe diver surveys themselves, the intention had been to carry out a single survey. We put SmartBall through the pipeline. The branch connection was going to be the intermediate branch connection that had caused us to have to split the SmartBall survey was going to be throttled back for the passage of pipe diver. So the tool was released, and unfortunately, the nature of the launch assembly, there was a problem during the first run. And actually pipe diver reversed in the pipe as it joined from the side branch. It flipped, reversed and backed down the pipeline. It stopped about 700 meters down the pipeline. And actually what you can see on the picture on the right is an image taken with an ROV that was used during recovery of that tool. You can see the tip of one of the petals is actually jammed in the pipe joint. That was about 700 meters from the start point, but it was able to be located immediately. So during the survey, we knew that it hadn't reached the first tracking point. We were able to locate it immediately using a line finder and confirm its location using a Sahara CCTV survey in the next few days. But we realised what had happened and then came up with a plan. So deployed an ROV from the reservoir 700 meters down the pipeline, used a lasso to put a noose over the nose of the pipe diver and pull it back out of the pipeline. So once it was extracted, we'll plan a repeat of that survey. So the second survey took place. Obviously, we put measures in place to launch it slightly differently. There were some slight changes made to the way the launch procedure was operated. No problems with that at all. Pipe diver left, went on, carried out a survey of the first 9 kilometres. Again, unfortunately, stopped unexpectedly just before one of the intermediate butterfly valves, just before the major branch connection on the pipeline. Again, it was located immediately. We were able to identify exactly where it was. We used Sahara CCTV to find out what the nature of the problem was. And in this case, it turned out there were actually two large pieces of timber partially blocking the pipe at that location. So something that, you know, without having done complete CCTV survey of the whole pipeline in advance, it'd probably been unlikely to have been able to pick that up. Obviously, nobody within Scottish Water Operations had any knowledge of the fact that this timber was there. And actually what happened was Pipe Diver sort of got stuck on that and wrapped around it slightly. So we had to develop another recovery plan. This one's slightly more complicated. So as I say, there's a 32-step recovery plan, which we developed, successfully implemented. So I think the key here was that, you know, we worked together both with Scottish Water, so WRC working with Scottish Water and Xylem to ensure that we had a really robust recovery plan. Only caused more challenge because of the beast from the east. You may remember the beast from the east a few years back happened to hit exactly the day that we planned to carry out the recovery. So we had to delay for a month, as it turned out. Pipe Diver was recovered. Data was retrieved for that first 9-kilometre section, despite the fact it was in the pipeline for an extended period. The data was still available, so we had that information. It was relaunched. And we were able to use an existing fitting on the pipeline, which was immediately downstream of where it had stopped, which was thankfully very lucky. And you can see there the fittings that were put in place to allow us to relaunch Pipe Diver into the pipeline. That survey was carried out, travelled successfully down the final 7 kilometres. Data was collected off the tool, and gave us some really good information then about the condition of that pipeline. So a summary then of those surveys. The Smart Wall and Pipe Diver surveys were ultimately completed successfully, the full 16 kilometres of the pipeline. There were, as I mentioned, some unexpected challenges, but I think what showed was the partnership between Scottish Water, WRC, Xylem, and I think mentioned here to Fastflow as well, the contractor who sort of carried out great works to install the various fittings that were required to ensure that we had ultimate success in recovering the tools, but most importantly the data, so that we had the data for that information. For each of the surveys, once the survey was completed, the tools downloaded and the survey data went back to Pure Technology Xylem in Canada for analysis, and they're able to bring their wealth of knowledge of the survey techniques, analysing the data, and really understand exactly what the condition of those pipelines are. Clearly, once you have the analysis of the data, it allows a targeted plan for the next steps. At that point, I'm going to hand over to Warren from Xylem, who's going to tell us about the engineering analysis and the results that were gleaned from the work.
Thank you very much, Anne, and good morning to everyone. My name is Warren, and I'm a condition assessment engineer at Xylem. And I'm going to talk to you a little bit about the engineering analysis first, and then we'll move into what everybody is here for, the acoustic fibre optic system. I think that it's important to preface what we've said just before with the risk assessment and talking about Scottish Water and sort of their perspective on the whole project, and then working into the surveys, and now me speaking about the engineering analysis, because that all that has to happen essentially before we're doing something like an acoustic fibre optic system. This isn't something that you just jump on straight away. You build up a little bit of information and you learn more about your pipeline, and then you'll get to something like an acoustic fibre optic system, which I'll speak about in just a moment. So let me speak about the engineering analysis first. So Scottish Water at this point have developed their risk assessment and identified which assets are low risk and which assets are high risk. Blairlinnans being one of the high risk assets. From there, if we're looking at this infograph of asset management, we're sort of working into quadrant 2, which is the inspection and the monitoring, because we need to validate what we've seen in the risk register or sort of the risk assessment. Because at the moment you might look at things like, diameter, redundancy, age, material, but without doing the inspection and monitoring, you don't really know what the condition of that pipe is just yet. But even that, so quadrant 2 is the inspection and the monitoring, but that is just data at this point, right? So we've done a smart bore survey, we've done a pipe diver survey, so we know about the leaks, we know about the gas pockets, and now we've found out about the wire breaks through our pre-stressed concrete pipeline. However, the real insights from that condition, from that monitoring, from that inspections, those surveys, comes in quadrant 3, which is the analysis and the modelling. So that's the important information that shows, you know, what we do with it next. You know, what does 5 pre-stressed concrete wire breaks mean? What does 10 mean? When do we have to intervene? When we're looking at leaks, is 5 leaks, 10 leaks, 20 leaks, like what does all this information mean? And then that's where we move into the engineering analysis. So, sorry, just going to remove this from the screen. So the engineering analysis has typically 4 deliverables: the hydraulic analysis, the design check, the finite element analysis, and the remaining useful life analysis. So 4 there. The hydraulic analysis looks at the static and the dynamic pressures of the system to give you a pipe by pipe pressure distribution. That can be also combined with a transient pressure analysis, which we always recommend for inspecting any of these pipelines. So what we do in that instance is put out transient pressure monitors, because the pressure monitoring system of most pipelines only takes records every 30 seconds, 1 minute, 5 minutes, whatever that may be. But what we're interested in is the surge. So we can make conservative estimates of what that surge might be if we don't have any transient pressure monitoring. But what we like to do is put them on and understand what it is, because these wires are going to break at a particular pressure, but it's the pressure waves that go through that's likely to really break the most of them. So that's what we can encompass in the hydraulic analysis as well. We also do a design check where we consider the material of the pipeline, the class, and different forces that are acting both internally and externally to understand whether this pipeline was designed correctly. It's more of a formality than anything, and we don't find many pipes that were more or less designed incorrectly, especially in the UK. Next, we move on to the finite element analysis, which is us building a 3D structural model of the pipeline using each layer and the mechanical properties of each layer. So as Ant mentioned before, we've got different concrete and steel and pre-stressing wires and mortar coating on the outside of pre-stressed concrete pipelines. We have a look at that all together, slice it all up, and with the 3D model, apply different scenarios of different pressures and different amounts of wire breaks to understand what the structural performance is over in different scenarios. And I'll talk about that just in a moment. Last is the remaining useful life analysis. So this is looking at the current level of distress of the pipeline from the inspections, and also looking at a predefined intervention level. So that is a level that is assigned by the utility. So it might be when the pipe starts to yield, or it might be before or after that point, and develop a probability curve or a probability chart of how many pipes we expect to be in a sort of high risk zone, or a medium risk zone, or a low risk zone. So let me first of all jump into what that remaining useful life analysis looks like. Here's an example. This one isn't Blairlinnans, but here's an example of what one might look like. So you can see we've cast out 5, 10, 15, 20 years and so forth. And this is what you see based on Xylem's experience with pre-stressed concrete pipelines and our extensive library and understanding of the deterioration rates of these pipes, as well as literature on what we see in literature and what they've studied. You can see that it goes from sort of 2 to 7 to 8 to 9 high probability pipes, and this might be high probability of reaching the yield point. And with no intervention whatsoever, slowly over time, the pipeline's going to deteriorate and you'll get more and more of those pipe sections. The idea here is that we get to a point, 5 years, 10 years, that we can intervene before it gets too bad, fix those pipelines, and so they've sort of transitioned into sort of amber or green sections, and we fix pipelines as they become as they reach the end of their life, essentially. I want to talk about the structural performance curves as well. So this is the output of the finite element analysis. And I mentioned before, we've got wire breaks along the x-axis and pressure along the y-axis. So two things we can measure, the wire breaks from the pipe diver and the pressure from pressure monitors and the transient pressure analysis that we've done in the hydraulic analysis. And so we've sliced the pipe up after making this 3D model and ran many scenarios about wire breaks and pressures and developed these curves. So at some point, as you transition from more wire breaks or higher pressure, we've transitioned to micro cracking and visible cracking. And at some point, that pipeline is going to reach its plastic deformation limit and yield. Then we've also plotted the ultimate strength, at which point the pipeline fails. Had a look at the operating pressure as well as the operating pressure plus a surge capacity as well. So this is really where the benefit of the engineering analysis comes in. We've looked at SmartVault, we've looked at pipe diver, we've got the data back. What does it all mean? This is what it means. This is something that a water utility can make actionable decisions on. As more wires break, we transition into a zone that's higher risk and we can take action. This is something that the data alone cannot show you. So much so that for Blairlinnans specifically, we did identify a section of pipes in a particular area that were in this red zone that had passed their yield point. And with meticulous planning on Scottish Water's behalf, they were able to create a bypass line. And I know we said before that this pipeline couldn't be taken out of operation, and it essentially couldn't, but these pipes sections were in such bad condition that they need to be actioned. So a pipeline was placed next to the current Blairlinnans pipeline and just turned off for a very short time, connected in, and we bypassed all those sections. And so that's something that, look, you wouldn't be able to get from just the engineering analysis. You wouldn't be able to get from just the data itself. You wouldn't be able to get from just a desktop study. It was the combination of these curves and the data that we got from the pipeline, so pipe diver survey, that allowed us to essentially replace these pipes before they failed. So we've spoken a little bit about the project and how it came to be, about the surveys themselves, and now the engineering analysis that identified the pipes, which pipes are good and which pipes are bad. But ultimately, as Ant mentioned, the long-term monitoring is the sort of big question. You know, we've done one pipe diver survey. That's one point in time that we have data for. What's going to happen in 1 month, 6 months, 1 year, 5 years? And that's where the acoustic fibre optic system comes into play. And so I'm going to talk about that in just a moment. Before we do, and we're going to have a quick 10-minute break. I just want to remind everyone, if they can please submit their questions into the Q&A box in the chat. We can come back to it at the very end when we have our Q&A session. We can answer all of those. So hang tight and we'll be back soon. Thank you. Thank you. And so we're back and audio is good as well. Beautiful. Hello, everyone, and welcome back. Thanks for submitting your questions. We've had a quick look at the chat and we'll answer them during the Q&A session at the very end. Thank you very much for your engagement. We really appreciate it. There's some awesome questions in there. So now I want to speak about the acoustic fibre optic system, which is, I guess, what a lot of people are here to understand a little bit more about, because it's a pretty fascinating system. Before the break, I spoke very briefly about the fact that pipe diver combined with the engineering analysis and SmartVault for that matter will give you a snapshot in time. Will give you a point in time of where your wire breaks are, and you can understand, what the pressure is. So we're sort of sitting somewhere on that graph, on that structural performance curve. The question is, what's going to happen in 5 days? What's going to happen in 6 months, a year, 5 years? And that's where Xylem, or Pure Technologies, found a need for something a little bit more real time, like a monitoring device, rather than just a quick survey once in time. And that's where the SoundPrint acoustic fibre optic system comes into play. So I want to just do a really quick recap before we get into things about pre-stressed concrete pipe. So it's got the innermost concrete layer surrounded by a thin steel pipe, which acts as a moisture barrier. There might be a second concrete layer, and that is wrapped in the high tension wires helically around the pipe. And that is the main structural component of the pipe that we're looking at. And that's what Pipe Diver looks for. And that's what AFO listens for those wire breaks. All of that is protected by an outer mortar coating. These are what those pre-stressed wires look like. There's not much to this slide other than a couple of photos. Don't worry, none of these were Blairlinnans, so Blairlinnans hasn't ruptured the whole barrel and burst into oblivion. I just wanted to show what the pre-stressed wires look like, because if you haven't had a lot of experience with these, it's just interesting to conceptualize like the look of them and the feel of them. So what is SoundPrint acoustic fiber optic system? So it is an inline continuous monitoring system of wire breaks as they occur using optic fiber. So optic fiber obviously uses light, and with the optic fiber system, it detects the sound and the location of those wires breaking. This system is exclusively and specifically designed for pre-stressed concrete pipes, so it's not applicable to metallic pipes. I'm going to categorize the components of AFO into sort of 3 categories here. I know my global product managers might slap me around a little bit for saying 3 only, because it is a lot more complex than that, but I feel like for the purposes of this presentation, 3 will do. So we've got the optic fiber cable itself. So it's actually 4 cables for the Blairlinnans pipeline. We can have more, but there's 4 optic fiber cables surrounded in a jacket. There's 2 spare. There's 1 for listening listening for the wire break, and 1 for locating where that wire break was within the pipeline. We have the entry and the exit points and the junction box. So that's where we might run the cable to a particular point. It might be an air valve, it might be some other intermediate point, and the cable comes out of the pipe, gets spliced together, and then heads back into the pipe. And that's for maintenance purposes, or it might be to get from one side of a inline valve to the other. I'll speak about that a little bit more in a second, but that's essentially that component there. And last but not least, we have the data acquisition unit, or the DAQ, or the DAC. I might refer to it, might use those terms interchangeably, I'm sorry. But that is the brains of the system. That is where signals of light get sent. That's where signals get received. That's where the power is. That's where the cellular connection to the network is that sends information to our data analysts and so on. So one data acquisition unit can be used per 20 kilometers of cable. If you've got more, obviously you install a second one, third one, fourth one, which we do have systems around the world where they've got multiple data acquisition units in their system. But for Blairlinnans, because it was 16 kilometers, we only required 1. You might be asking, is the cable okay? Is it safe to put inside a drinking water pipeline? And the answer is yes. So testing was done in accordance with the DWI Advice Sheet 8, which is about small surface area products in drinking water pipelines. And that looks at contact area as well as the static water volume and the contact time with that particular product with the water. And as per the advice sheet, we performed our British Standard 6920 testing, and the cable met the requirements for odour, flavour, and the growth of microorganisms. So for now, we've spoken about the pre-stressed wires. We've had a look at the AFO system and its components. We've also spoken about the compatibility with drinking water. I want to speak a little bit now about the process. So what happens when a wire breaks? What's next for ourselves, for the system, for the utility? I want to speak about the hub, which is the system that captures all of that information. And then the planning and deployment of putting in something like this AFO system. So here's the process. So first of all, we have a wire fail. This is once it's installed, remember. We have a wire fail. That sound is very unique. It's got a very unique acoustic signature, okay? So it's not like any other sort of sound that you could typically hear with a pipe if it's just flowing off this turbulent flow, or even if somebody is doing work above the main, which we have seen in instances where there might be some construction going on. Our wire has picked up an acoustic scent, but it's not indicative of a wire break or a wire fail. In those instances, we still call up the utility and say, hey, there's something happening above the pipe. You might want to go check it out, just in case there was some construction happening nearby that they didn't know about. Once that wire fails, it's picked up by the data acquisition center, so the data acquisition unit, and then the acoustic data and the location data are sent remotely to our data analysts. And with the help of machine learning, they categorize that as an event of interest or a wire break, which gets sent to the utility. And so how does that get sent to the utility? First of all, let's just disregard step 4 for a moment. All we need to know that that particular wire break is mapped to a particular pipe. Then an email alert goes out to the asset owner and anyone else on the mailing list. For example, I'm on the Blairlinnans mailing list, so I get those wire break email alerts as well. And lastly, that data becomes available on the secure GIS website for anyone to see who's got access. So I want to talk a little bit more about that step 6, about the GIS website and what we can see on it. So we've labeled it the hub. It is called the hub. And here there's a lot of stuff on the screen, so I'm going to talk through it just quickly. We have a pipe by pipe map, and it has every single pipe in our pipeline, and they're all color coded. So that's the part 2 that we see here. But you can click on any individual pipe and find out more information about it as well. So for example, in number 1, it's got our pipe 4287. You can see the pressure of that pipe based on the hydraulic analysis. You can see it's sort of transitioning from a higher pressure to a lower pressure area. It's got 5 + 1 = 6. That's 5 wire breaks picked up by our electromagnetic inspection, the pipe diver survey, plus 1, as in 1 wire break picked up from the AFO system = 6. 5 is going to stay the same because that was the pipe dive done once upon a time. That 1 will turn into 2, turn into 3, turn into 4, and so on as the AFO system picks up more wire breaks. So that's a good little snapshot that we have for each pipe section at the top of the page. It's good also to know what's happening either side of that pipe. Do you have a lot of wire breaks happening either side? Do you not have wire breaks happening either side? Just good information to know. So that's 1 and that's 2. 3 is the structural performance curves that I spoke about before in the engineering analysis. And they've got, remember, the wire breaks on the x-axis and the pressure on the y-axis. Each pipe, depending on the elevation and where it's situated within the pipeline, it's going to have a different pressure. And we know that the wire breaks are going to be different. As each wire break occurs, that dot slowly transitions from the micro cracking and the visible cracking into the yielding area and the failing area. So that's a great snapshot for a pipe by pipe as well. And last but not least, we have the wire break trend. So this is an example only. This is not a pipe section from Blairlinnans. But you can see that the trend of these is sometimes exponential, and it's completely random at some points. You can see that we get 5 wire breaks in the span of, I believe that's a year, maybe even longer. And then it goes from 5 to almost 25 in a matter of a month. If you were to inspect that once every 5 years, you could easily miss it. You could look at that pipe and say, there are 0 wire breaks. Why do anything about that particular pipe? It's only with the acoustic fiber optic system that you can track it day by day and see where that trend's heading. If an exponential trend does occur and multiple wire breaks happen at once, that can be cause for intervention. The utility can go out and action that pipe and have a look at it and say, yep, that's in bad nick. We need to replace it immediately. So that is a little bit of what the information that's available on the hub. Up on the left-hand side, there's a panel of extra information that can be there as well. Other pipe specifications, some of the leak detection information from the smart ball, and so on. So let's talk a little bit about planning. how do you put 16 kilometers worth of optic fiber cable into a meter, essentially a meter diameter pipeline? The answer is not easy, but always worthwhile. At the very start of the system, we're inserting it into an air valve just outside the water treatment works. The very end of the system is where the extraction tapping for the pipe diver was, and that's where the data acquisition unit is situated. In this picture, there's only one and then two loops. In actual fact, for Blairlinnans, there was 11 separate runs, and so those 11 separate runs are intermediate and separated by maybe air valves or other features, because for maintenance and for just installation in general, you don't want to run a huge length of cable. That makes it very difficult if you have to replace a section of pipe or do any work there, and the installation of itself becomes more difficult and more tricky. Imagine trying to put the cable in, and the more bends there are, the more sort of friction there is. It's not a good option, and so we try to break it up into smaller sections that are more manageable. The longest in this case for Blairlinnans was just over 2 kilometers long. So let's talk about the deployment itself. So step one, we need to get the cable into and out of the pipe. And so we install these insertion stacks, which I mentioned at the very start of the talk about the AFO system. So they can be tapped directly into and out of the pipe itself, like we see on the left-hand side, or they can be through a flange connection, tapping through the flange connection. Usually, it just depends what features we have there at what particular point in time. There might be an existing air valve, and we'll create a custom flange with the air valve moved to the side instead of directly through, so we can make way for the insertion and the insertion point and the extraction point from the pipeline. And now we have to run the cable. So you can imagine, if you can imagine, two big spool pieces, one with a cord or a string and one with an optic fiber cable on it. To put the optic fiber cable in, we first run the string through the pipe. And so that involves setting up a tripod like you see in this picture, inserting this cord with a parachute on the end into the flow. The parachute opens with the flow, gets caught and pulled along as we feed the string in. And at the other end, the downstream end, we have a extraction stack, which has a camera on it, much like the pipe diver or the smart ball net. And we have a hook on it. And once we see the parachute come close, we can hook it, pull it out, and pull the cord behind it. So now you've got one continuous bit of cord from your insertion, the start of your insertion, to the end of your extraction. We hook the cord to the optic fiber cable and then run it in behind and pull it through. And that's how essentially we pull the optic fiber cable through. That was not always smooth in the case of Blairlinnans. The piece between the cord itself and the optic fiber cable came loose multiple times. And so what you do was pull the whole string through. Everything's looking great. Go to pull the optic fiber cable through and they would come apart. So you pull the string out and then there was no optic fiber cable on the end. But luckily this optic fiber cable was attached to the spool, but it meant that you had to rewind it back up and start the whole thing again with launching the string. Luckily that was an area of improvement that we identified, and that piece has now changed and there aren't any issues anymore. The next step is splicing the cables together. So as we pull the cable into and out of the pipe, we launch the next section, launch the next section, launch the next section. But behind that, we splice the cables together. And so that involves, so the picture on the left-hand side is just adequate amounts of cable that's left over from a run. And what you see on the right-hand side is the finished product. So it's protected by a plastic sheath, and it sits inside a junction box, and the cables are spliced together inside that box. And last but not least, it's the commissioning stage. So there is now a 16-kilometre stretch of optic fibre cable through the pipeline, and the data acquisition unit is set up. It can listen for wire breaks, but at this point in time, it doesn't know where those wire breaks are occurring. It can hear them, but we need to calibrate the whole thing. And so what we do is what we call impact tests, where we're knocking and simulating wire breaks at different points along the pipeline, typically at those splice points, and that will calibrate the system with the help of our analysts who are on the other end, having a look at what the wire breaks are doing and what the data acquisition unit is telling them to calibrate exactly where the pipe is, so the cable is within the pipe, because that's obviously very important. Last part I wanted to touch on was about protecting the cable. So there are two kinds of systems we can have, unanchored and anchored systems. If we need to anchor the system, for example, if there's a large branch like you see in the left-handmost photo, we don't want the cable, smashing about and flopping around. So it needs to get anchored on the pipe. Also, likewise, if there's a tight bend, if there's a miter joint, we don't want wear and tear on the cable. So we will get Penflex tubing, which is essentially a corrugated metallic tubing that's got some flexibility, and run the cable through there and around corners. Last picture on the right-hand side is a butterfly valve that we have. And so that's less about protection of the cable itself, because with these anchoring points, but more just having to think about, okay, if there's an inline valve, we can't close the valve if we've got a cable through it. And so we will take the cable out before the valve, run it externally, and then put it back in. So that's an important part as well. So we had a look at what SoundPrint Acoustic Fibre Optic system is, had a look at the components, the compatibility with the drinking water, a bit of the process and the online system, the hub, which captures all the data, the planning, deployment, and protection. I tried my hardest not to talk too much about the benefits because I'll leave that to Ian. Thank you.
Thanks, Warren. Well, now that you've heard from the two clever people in the room, I'm afraid you're back to me for the outcome. So how are Scottish Water using the information that we have from this project? So ongoing monitoring, as well as Warren, somehow nice to know that he's also getting emails, same as I do. My team have a team mailbox that the wire break reports come through to. So we monitor every time a wire break comes through. We check the pipe, check the surrounding pipes to make sure if we have any pipes that are approaching any of the intervention points that we've agreed with the business. Because we have these finite element analysis condition curves, as the picture on the right there, for each pipe stick, when what we've done is we've actually agreed threshold intervention levels. So if a pipe's in the first zone there before it crosses the green line, we're absolutely fine with that. When a pipe segment crosses the green line into the amber area, what we'll do is we'll actually go away and create a work pack for that specific piece of pipe as to how we would repair it. So down to what valves we have to shut, what we need to tell, if there's any treatment works, interventions that need to be done, any customers that would go out of water, where we would access, where the nearest road access is, if we have to cross anybody's land, all these kind of things, anything we know about. Potential challenges, is it a rocky area? Is it somewhere where it's particularly high pressure? So we will create a bespoke work pack for each individual pipe element that goes into that amber zone, and these then get kept should they be needed in the future. Now, if a pipe continues through the amber zone and crosses the boundary into the red zone, it's crossed the yield barriers, it doesn't mean it's immediately going to fail. So that red line up at the sort of top right of the diagram is where we're predicting the pipe will actually fail. So when a pipe enters that red zone, that's when we're going to action the work packs that we have prepared. So it means that we're doing all this in a very planned way. We know access requirements, shut requirements, any DOMs, which is our distribution and operational maintenance strategy, any things we need to do with the network to enable the repairs to happen, how we're going to carry out the repairs. We know all of that in advance before we decide to go out to site to do anything about it. And because of the way the Blairlinnans system is set up, we've talked previously about this major branch that goes off to feed a fairly large area. The system effectively works in two functional lengths. You have a before the branch and after the branch, essentially. And the impact of failures in each of those areas is different. So what we have is some more generic packs created. So if it fails, if we get an area before the branch, this is what you do. And if you get an area after the branch, this is what you do. It doesn't have the details about, ground conditions, landowner, things like that. But it means that we can use these plans with our intelligent control center. So if anything happens, a burst or, someone comes out and there's third party damage to their main, they have a pre-prepared, how do we fix this pipe plan in place. Again, it won't have all the details that the ones that we're working through the AFO has, but it's certainly a better position than we have been in for the first 40 odd years of this pipe's life. In terms of outcomes, this is very much seen as a good news story in Scottish Water. I wouldn't be standing here talking to you now if it wasn't a good news story. The simple fact that we went through a number of challenges and redid the work. We talked earlier about the pipe diver getting caught in the pipe and then finding the pieces of wood that blocked it. A time in the past, if we'd come up with these kind of challenges in such a crucial main that has such a high impact, it would have scared people off in the business. We just can't do that because there's too much risk. But the fact that we perceived through those setbacks, we're now at the other side. We've shown a capital and carbon cost reduction based on other intervention options we looked at. Obviously, if there are elements that do need to be repaired, we will do those on an individual basis. So some of the elements we looked at in that options assessment, still may come to pass. We may need to do some local diversions. We may need to do a partial replacement, but we will have the evidence in hand to enable us to say, here's exactly why we need to do it, and here's exactly the bits of pipe we need to do it on, rather than the first half of the pipe, the second half of the pipe, which was about as far in detail we could have gone before. We're utilising an existing asset, 90+% of which is in great condition. I mean, the big news story for me from this survey was we had circa 8,000 individual pipe elements, and the number of them that were of a concern to us was 24. So 24 out of 8,000 is a very good number. And most of those 24 we dealt with the bypass Warren mentioned earlier down at a place called Milton, where we there was a lot of sleepless nights and a lot of things went in place to try and enable us to do that work, to do the tie-ins for it. It certainly wasn't a comfortable position and not something we'd like to repeat anytime soon. But the fact that we could go in and do it in a planned manner meant we could do as much as we can in advance to prevent having an impact on customers. If that pipe had just failed suddenly, we wouldn't have had time to put those other things in place, and it would have a much higher impact on our customers. We can now monitor the condition over time. These emails come through to me on a regular basis. We look, and there has been times when something has come up as a potential emerging issue. We've gone and looked into it, and either the pipe has thought better of itself and maybe started behaving a little better, or whatever it has been, that it hasn't come to that. But we can now see on a live basis where we may need to do work in the future. And that granular basis is key here, because in a 16-kilometre pipe, we were looking at 50 metres of it or something, 50, 60 metres of it was actually a potential issue. So if we can go in and do these targeted interventions, it massively increases the benefit for our customers, because we're spending money efficiently, that we're not spending carbon or capital costs that we could be avoided. And it means that we get that planning element in place. There's always the potential for something to happen. I mean, the first rule of water industry is that you never know what's around the corners. Something can always happen. Somebody can go to dig a hole, and we had a couple of months ago a farmer putting in fence posts, and he put an auger through a trunk line in his field that he hadn't checked if it was there. You're never going to get rid of that. There's always going to be risks involved. But having this system in place, we're managing all the risks that we can manage to the highest level that we can, and that allows us to provide a number of benefits for our customers. And again, it gives us the best chance possible of making sure that our customers, when they go to the tap, clean, safe water comes out of it, which at the end of the day is our kind of primary function here in Scottish Water. Thank you all for your attention so far. We're about to set up for the Q&A, so the camera and the sound will be going off for a minute or so as we dance around the room to our new setup that we're going to have. So if you bear with us a minute, we'll be back with you shortly for the Q&A session.
Fabulous. Okay, thank you everybody for all the questions so far. So Imelda here, I'm off camera. I'm going to be moderating the Q&A and asking these kind of questions to the panel. So if you do want to keep them coming in on the chat, we'll be able to see. I was just saying in the break that we've had this is probably the most questions I've seen on a showcase. That's really great about how engaging everybody's been. So the first question comes from James Young, and this question is, how many years experience does your company have in checking pre-stressed concrete mains, and what size of mains? And I thought, Warren, if you'd like to pick that one up.
Yeah, certainly. So thank you for the question. It's something I didn't mention during the presentation, that, this is typically described as an innovation thing, but Pure Technologies and the Acoustic Fibre Optic system, as well as Smart Ball and Pipe Diver, have been around for about 15 years. Oh, sorry, over 15 years. And we have acoustic fibre optic systems globally. There's about, I think there's about 1,500 kilometres worldwide, and they've detected something like 100,000 wire breaks globally. So this is something that is well established. It originated in North America and it is slowly spread globally.
Amazing. Thank you so much for that, Warren. Okay, so Ian, I think this next one is going to be for you. So we've got a question here from Anne-Louise from Portsmouth Water in Asset Management. So the Excavate 4, how are you accounting for costs following the results? So if, for example, the condition assessment assesses that the investment level needs to be an imminent partial replacement, there is no allocation of capital for that. So how do you deal with ongoing costs following a determination of quality of the pipeline?
Thanks for that. I can partially cover that towards the end, but I appreciate this question from Ella. So the first step is to monitor it, to know what the condition and the issues are. Because of the management approaches, how we're funded now is that if I can go to it's called the investment group or the Scottish Water Board, depending on the value of the project, I now have the documentary evidence to say this pipe has passed its yield limit, this pipe needs to be replaced, here's the risks if it fails in service, here's how we would do it, and here's what it will cost, and I can then go for funding for those projects. It's the primary purpose of this is, historically, we tended to be a little bit more of a blunt tool than a scalpel in terms of, if parts of a pipe are failing, we would replace the whole pipe. Now we have the ability to go in and say it's actually only these 2, 5, 12, whatever pipe elements that need to be replaced. So we can plan that and go in and do it. So it's a significantly lower cost. But yeah, the way it's funded would be that I would just make an application through my management reports to say I need more money on my management report. It goes up to the water board and they would then make a decision as to whether or not this was higher priority than any of the other works that were ongoing.
Amazing, thank you for that one. Okay, so I've got a question here for Anthony. So this is from Sonia. So what's your recommendation to manage the existing gas pockets in the system before an inspection? So 1, don't purge the main so Smart Ball can detect the location of gas pockets, or 2, purge the main so Pipe Driver can collect the condition of the pipe at the crown.
Okay, so typically you wouldn't purge them. Obviously, you'd hope that your air valves are all working and functioning correctly, and there wouldn't be gas pockets in the pipeline anyway. The Smart Ball is unaffected. Obviously, will detect them because it'll hear the surface noise that's generated by the gas pocket at the gas pocket. Pipe Diver will actually work even with a gas pocket in the line. So as long as it's not a significant reduction in the cross section, it's just a small pocket at the top. No problem with Pipe Diver working through that. So yeah, no particular issue. No need to make any specific actions for the surveys. Clearly, once you know they're there, you might want to take action just to resolve it.
Fabulous. Okay, Warren, I've got some questions for you. I'm going to kind of put them a couple together. So we've got a question here from Michael. Does the Smart Ball cause any increase in turbidity? And then a couple on flow. So Anne-Louise said it appears to be rolling on the invert with a significant flow draw into the centre of the velocity profile. Is this a problem? Also, what operational conditions are required, e.g. bidirectional flow? Another question on flow in terms of the minimum flow velocity required to ensure a successful survey for both Smart Ball and Pipe Driver. And then another one saying the maximum flow also, the smallest diameter that we survey, please. So lots of questions around flow.
I think there was maybe a part of the presentation that we should have put in there that we forgot about, which is about the flow. So Essentially, with Pipe Diver and with SmartBall, there is a minimum and a maximum flow rate that we can operate within. For this, let me start with the minimum as the maximums, and then we can go into the rolling of the SmartBall itself. So for SmartBall, in flat pipe, it needs to have a velocity of 0.15 meters per second minimum, right? Obviously, not much pipe is exactly flat, and as the slope increases, the velocity will need to increase to accommodate the ball rolling up that section of pipe. We've modeled the whole thing based on diameters, based on different gradients. We can traverse vertical sections of pipe, and we've got graphs that say for this diameter, you need this flow, for this diameter, you need this flow. That is all part of the planning process. That is pretty much one of the first things we look at. What flow can you get? What diameter is a pipe? Therefore, what velocity is the fluid going to be moving at? So I mentioned 0.15 for flat. For 45 sections, it's a bit more. Vertical sections, it's obviously more. The maximum velocity in the pipeline is, we don't like to go higher than 1.9 meters per second. That is really high. You don't come across too many pipelines that are going that quick. But even if they are, we're still able, like for example, we did a job just recently where there was a short section of pipeline that had a reduced diameter. And for that section of pipe, it was going through faster. But we knew where that section of pipe was. And even if it doesn't roll perfectly, it is still listening. It's still got the acoustic sensor in there, and it is still listening for both the gas pockets and the legs. So there's no issues. So that was the minimum and maximum flows. The other question was about the rolling of the ball itself and the turbidity. The SmartBall itself is a metallic core, but it's encased within a foam jacket. And so that foam jacket gives it a little bit of buoyancy. So it's rolling along the bottom still, but it's not like as if a rock is rolling along the bottom. Yes, it's going to be along the invert, and yes, if there is sediment there, it might push some sediment around, but we haven't had serious water quality complaints. You wouldn't expect it to stir up the sediment more so, because it travels at about 70% of the fluid flow. It's rolling slower than the flow is going past it, so you wouldn't expect it to kick up a lot of sediment. I hope that answers your question.
Just pick up perhaps on the pipe diver. I think you didn't mention the pipe diver velocities, but so pipe diver has, because it's completely neutrally buoyant in terms of movement, it doesn't require the same sort of flow, but you still need a minimum and maximum flow velocity to make sure the tool moves through the pipeline and gather the data in the best way. I think it's right in saying that so sort of typically half a meter a second to just over a meter a second is the sort of correct sort of range for pipe diver to give you the optimum data analysis. It's not so much about the transit of the tool, but more about making sure that the data it collects is collected in the best way.
Correct, yeah. So with pipe diver, it's a bit more reduced. With SmartBall, you can really go down the lower ends of flow and the higher ends of flow.
Thank you for that, guys. So, Ian, I have a question for you from Duncan Allen. Was the timber removed from the pipe as part of the recovery, or is it still a restriction in the pipe?
You've got to love when a colleague sends you a question. One of these things, thank you, Duncan. I will seek you out after this. And thank you in person. The timber was not removed. When we looked at it, the timber is an inert substance. It has been in the pipe for 40 plus years. The way the system currently is and where the timber is at this key junction, we would run the risk of cutting the water supply to around 40,000 people. And the risk of that for removal of something that's been in the pipe for nearly 50 years wasn't deemed high enough. There is currently a resilience project in flight in Scottish Water where we're going to put in a link that would allow us to isolate that without running the risk of these customers going out of water. Once that has been built and is in place and is usable, we would look to reconsider whether we go into the movement. But at the end of the day, I mean, it's been there for 50 years. There's no real risk to customers or anything. The only risk is to pipe divers. So as long as we don't plan to pipe diver it again anyway, so that we're just highly unlikely to cause us any issue.
Fantastic, thank you. Okay, so Anthony, I've got a couple of questions here that I'm kind of putting together. So I've got one from Anne Louise and one from James Young. So one, Anne Louise says, if it goes rogue, so if we say a branch was not closed off in time and technicians can't get to it, has this ever caused a blockage if the pipe is tapered right down, say a large consumer? And then James kind of similarly asked in terms of these kind of issues in regards to what happens to the smart ball, what if it gets stuck? Will it pick up the change in noise and if and when it passes a joint socket or previous repair? And same question, are the pipe driver passing over joints, sockets and previous repairs?
Okay. Yeah, so clearly one of the key aspects of these surveys is to ensure that you do the planning in best you can prior to releasing either smart ball or pipe diver. And the critical aspect there is to try and ensure that you have no unexpected or unknown branch connections. Now, clearly, as I mentioned during the talk, sometimes the records aren't quite as good as we'd like, and there is the potential that there could be an unknown branch connection, or operational difficulties. You know, somebody is planned to be at a particular location to shut a branch and they don't make it in time, or makes a mistake, shuts the wrong branch. So it can happen. Clearly, a lot of effort is put into ensuring that it doesn't happen. If the ball does get down a branch connection, yes, then ultimately it could pass on down through the distribution network and get to a point where it would cause a blockage. So that is a risk. No getting away from that. But as I say, the key thing is to carry out planning, to look at the documentation, to talk to local operators, because there's a wealth of knowledge within local operators as to where any branch connections, where any feeds are coming from. And that information is absolutely vital to ensuring that kind of thing doesn't occur. Both pipe diver and smart ball are emitting. Smart ball is emitting a tone every 3 seconds, which allows it to be tracked. Pipe diver similarly is not only emitting a tone that allows it to be tracked, but actually the signal that is used to inspect for the wire breaks creates a signal. All of that can be used to go and locate the tool, and part of the idea of the monitors that we mentioned during the talk, it allows you to understand where the tool has got to. So if it suddenly doesn't make it to the next tracking point, you already have a very good understanding as to which section of pipe it's within, and therefore you can start honing down on where it might be and use sensors to go and perhaps sort of move them around, put them onto local sections of pipe so that you can actually pinpoint very rapidly where the tool has got to. Very unusual for the ball, well, either the ball or pipe diver to stop unexpectedly in the pipe. The timber was absolutely a completely unexpected feature. Yeah, sorry, I didn't quite get the business of sort of monitoring joints, but sort of just something that we haven't picked up again. Both the smart ball and pipe diver have magnetic sensors. Pipe diver's using that to detect the wire breaks, but they have magnetic sensors which actually pick up as it passes every joint in the pipeline. So that has a specific magnetic signature, so we can see those joints in the data. So I think that might possibly answer the other part of the question, but that might inspire just a bunch of other questions.
I just want to add one quick section to that as well. We would not put anything into a pipe unless we were confident that we could get it out. We don't want to get smart ball and pipe diver stuck in the pipe. The asset owners, the utilities don't want to get anything stuck in the pipe as well. And it all comes down to planning. Meticulous planning is what is going to allow for a successful survey. And there's always a risk with everything. But what you have to ask yourself, sort of, what risk is greater? Is it the risk of not knowing the condition of your pipe greater, or the risk of putting pipe diver in and getting stuck greater?
And I think, yeah, coming back on that is the prior to launch, we have a risk register for the contract, so we're all looking at what are the risks associated with this, and one of those is the operational risks of releasing something into the pipeline. And prior to launch, then all parties have to accept and sign up to say, look, we've gone through the planning process, we've used the best available information, we've looked at all the sources of information. Are we happy that we've covered all of the known risks for this pipeline, and that's a clear step within the contract process to ensure that that is signed off by all parties before moving on to carrying the survey.
Big thing for us actually at Scottish Water, and it was something that you come against some resistance at times when you want to inspect an asset that is critical, because from an operations team standpoint, they don't want you doing anything that might cause an issue with their asset, and that's completely understandable. The key thing here is, would you rather deal with it knowing, you know, we're going to do a piece of work that, yes, there's something may go wrong, but we know we're planned for it, we have spares in place, we have all this. Would you rather that, or would you rather we just didn't know how bad this asset was, and then at 2 o'clock on a Sunday morning, you're getting called out of your bed to go and deal with something? You know, it's a balance. We shouldn't be doing anything that creates an unnecessary level of risk. But the kind of risks we're talking about here are manageable as far as possible through best practice and making sure we do the work right. And as Anne and Warren have both said, the risk of doing nothing is far higher. The risk of not knowing what the condition of the pipe is, the risk of having a failure. I mean, pre-stressed concrete pipes, one of the things with the gas pockets are, that's when a pre-stressed concrete pipe potentially fails explosive. And that's where you get you're looking at debris zones, you're looking at crater sizes, and they're very scary words to look at when you're doing risk assessments and what might happen. This enables us to remove those risks, and it enables us to manage the likelihood of that going forward. And that's far more important than, you know, with the best will in the world, if we block a pipe and some people's water goes off for a short period while we retrieve the smart ball, the risk of that happening versus the risk of a catastrophic failure of a key trunk line, they're night and day.
Fabulous, some fantastic answers there, guys. Because I was going to ask something about risk as well. But I think you've already picked it up. So we have had a question come through from Luke Eels from Santec. And Anthony, I think maybe this is one for you, but also if anybody else wants to feed in, which says, did you conduct any CFD modelling analysis to get a better understanding of the downstream hydraulic performance, fibre optic cable movement and delta sediment lift after install, and the impact on the pre-stress pipe and the impact to the downstream supply network?
No.
Next question.
Well, ultimately, once the fibre is installed, actually there's very little movement of the fibre within the pipe. It's actually tensioned. So once it's installed, it's not left hanging loose in the pipe. It's actually tensioned for a number of reasons, but to prevent it moving and abrading, but also, obviously that means it's less likely to cause any problems. Actually, in this case, you've got a big service reservoir immediately downstream of the section that's being monitored by AFO anyway, and there would be a secondment time within that. But it's a very, very small. The movements that you would see within the pipe are very, very small anyway. You don't want the fibre moving about because it will abrade. So clearly, everything is done to try and reduce the movement, and therefore any chance of turbidity problems as a result of movement of fibre is really greatly reduced.
Fantastic, thank you. Okay, so we've got another question from Anne-Louise McGinn, and Warren, I'm going to direct on your way. So regarding transients, there are usually not very many fittings available for monitors, hence leakage detection being notoriously difficult. So how do you test transients where there may be no fittings available? If you can, is that a game changer? If you have no transient monitoring, can the analysis still be undertaken?
Yeah, so we fit transient pressure monitors where we can. If there are available fittings, great. If there are not, look, that exercise is obviously, it can't be done. And we'll use conservative estimates and estimates in literature and what we've seen in the past with similar pipelines to make an estimate. That is all documented, obviously, and in that structural performance curve that we see where we have maximum operating pressure and the max operating pressure plus surge, that'll be noted whether that was derived from an experimental analysis or whether that's a conservative estimate from literature or similar projects.
But even it doesn't require a massive connection to put on a transient monitor. So the air valve points, so even actually within the air valve itself, you might be able to fit a transient monitor. And you don't need hundreds of them. You only need a few along the full length of the pipeline just to pick up the
transient travel so far that you don't need It's not like every 500 metres you need one. They'll travel long distances, so you'll be able to see evidence of it, even if it was, if you were further away, you'd see a smaller amplitude of it, but you'd be aware that there's transit so that you could then, and if it came to it, you can almost go and potentially put fittings on the pipe if you have an area of concern.
Fabulous. And then I've got a question from Michael, another one from Luke, which I'm going to direct staying with you, Warren. What is the lag from a breakthrough analysis through to an alarm being sent? And also, what is the percentage rate of false positives that are being detected?
All right, cool. So I'll start with the alarms. So we use the wording near real-time wire breaks. We say near real time because once a wire breaks, the data acquisition unit sends that signal to our analysts. Our analysts are monitoring the system and all systems globally 24 hours a day. They are the last line of defense to have a look at that. Like I said before, with machine learning, we identify and categorize a wire break as a wire break or as something else. Once they do that, they are the ones who give it the all clear, give it a tick, and then that email will get sent. And they're monitoring 24 hours a day. We just want a person in that last line of defense. We could have it flick ping straight away to us, to Ian and Scottish Water, but we just want one person there to vet them before they go out. So it's near real time. It'd be in the order of minutes or an hour, type of thing. And what was it? What was the end of the other question?
False positives.
False positives, right? So with the electromagnetic inspection with Pipe Diver, we calibrate the unit and then we do the inspection, and it can pick up wire breaks, and we bundle them in groups of 5. So the electromagnetic inspection picks up 5, 10, 15. If it thinks it's 12 or if it thinks it's 13, we categorize those as 5, 10, 15. So that's the first thing you've got to remember. With AFO, once AFO goes in, that is picking up every single wire break as it happens. If we get to a point where it's past its yield limit, or the asset owner would like to replace or fix that pipe, one of the steps we do after excavating the pipe surface is use a similar device that Pipe Diver has, like another electromagnetic inspection device, to walk over the top of the pipe to locate, yes, that is the correct pipe. We've seen the number of wire breaks that we have from an analysis or from the monitoring matches the amount of wire breaks that we have on this pipe. And then we can make sure we excavate the right pipe, because there's nothing worse than going out and thinking that there's a pipe section and excavating that and it was the pipe next to it. As in terms of percentages of false positives, I wouldn't have an answer for you, sorry. That's sort of just the general process about how we do things and how we have levels of error that we incorporate into the inspection, into the monitoring, and then as a last line of defense, if we're going to replace a pipe or do any work on a pipe, we make sure we scan that pipe before we dig it up.
Fantastic, thank you for that. So guys, we've still got a couple more minutes of Q&A left, and so we are going to ask a couple more questions. Any questions that aren't picked up will be shared with the Xylem, Scottish Water and WRC team, and they'll be picked up post showcase. Just whilst we're all still online, we're just going to put a poll up, just asking for a little bit of feedback on this showcase, and also a really important metric there about how many of you intend to embed this knowledge within your organisation. So taking things that you've learned today and taking it away and actually applying those learnings within your organisation. So just going to carry on with a couple more questions, but wanted to put that up whilst everybody is still online. So my next question is for Ian. Are there any future plans to adapt the fibre optics to automate valves along the route to support with supply resilience?
At the risk of pulling an hand and giving a one-word answer, no. I mean, one of the key challenges with this pipe is there are only 3 valves and 16 kilometres of pipe, which is one of the key challenges we have around maintaining supplies if anything happens. Automation of valves is something we have in certain locations in Scottish Water. It's not something that's widespread. It tends to be more at operational sites. So there is scope for automation of valves at either end of the AFO system, but we don't currently have any plans to use the fibres for anything other than the purpose they're in for, which is to monitor the condition of the pipe.
Fantastic, thank you. Okay, so a couple of questions around kind of failures and replacements. So another one from Luke, which says, in the event of a large failure, what is the protocol to remove the fibre? Are you using specialised contractors, partners, or Scottish Water internal R&M teams? And did you make customers aware of the fibre install? And then kind of on that same kind of vein, how do you carry out a repair or replacement when the optic cable is in position? So if anyone wants to take that one.
Well, how we do the repairs is something we're doing a lot of work on at the minute. Traditionally, you would remove the piece of pipe and put another piece of pipe in. It's fairly straightforward. To do that, you have to remove the cable first. You would then have a shutdown, do the pipe repair, put the cable back through and you're back up and running again. Because we're looking to intervene as pipes get towards end of life rather than pipes have actually failed, we're actually looking at external repair methods that don't require the actual pipe itself to be replaced, but we can do there's some options there around retensioning or post-tensioning, where we essentially, the way it works in my head is like a giant Jubilee clip, but we're basically wrapping the piping cables and providing the strength that they'll keep the wires within the pipe did provide, but we're providing it externally. Those kind of repair methods would mean that we wouldn't need to remove the fibre. We could leave water in the pipe while we're doing it. One of the risks with pre-stressed concrete pipes, if you completely depressurize it, because the water is constantly pushing out and the wires are holding it in, if you take away that force pushing out, you can cause a number of wire breaks by depressurizing it. If we're doing that at the same time that we don't have the AFO system in place because we've removed the wire, we would potentially cause a number of wire breaks along our network that we wouldn't be recording. So depressurizing the system to replace a piece of pipe has a lot of potential knock-on risks associated with it. So if we can get an improved way of working, which we're currently in discussion with a number of suppliers about doing these external repairs, it could save us that risk. Obviously, if the pipe has actually failed and there's water escaping the pipe, at that point, these external solutions don't apply, and it would simply be a case of we need to take that. Unless it's a joint, we can maybe do some sort of encapsulation collar. If it is actually the barrel of the pipe partway along has failed, we will need to go down, and it would be a case of through our agreements with different framework suppliers, getting the cable removed, replacing the concrete section of the pipe, putting the cable back in, and recommissioning the AFO system.
Okay, fantastic. Right, I think that takes us to time. So thank you all for your kind of, amazing answers on the panel there, and for everybody in the chat being so engaging. We've had so many questions come in. There are still quite a lot that are kind of due to be picked up. So I'm going to pass that over to our very, knowledgeable panel, and they will be able to pick it up post showcase. If you haven't already, please do complete the poll, just letting us know how you've found today's session. It's really great feedback for ourselves and for kind of Xylem, Scottish Water and the WRC teams. This recording will go live on the Spring platform alongside a case study. Usually goes up within a week or so, and you will get an email notification of that. And if you follow us on LinkedIn, then there'll be one there also. So just want to say thank you to everybody, and thank you to the Xylem, WRC and Scottish Water teams, and thank you all for attending today.